In this video, we're going to actually use our knowledge of the solution of the electrical potential for a point charge to solve some problems. This problem says calculate the electrical potential at point P, which is down here, at 0 meters in the X minus 0.45 meters in the Y due to a 6 nanocoulomb point charge, which is located 0.15 meters above the x-axis, and a minus 4 nanocoulomb point charge that is located minus 0.45 meters along the x-axis. Now to do this, we simply add up the solutions for our point charge. So I'm going to first say that V1 is equal to K times Q1, and I'll call this Q1, divided by R1. This is 9 times 10 to the 9th Newton meter squared per Coulomb squared times 6 by 10 to the minus 9 coulombs. Very convenient because it cancels this. All of this divided by the distance. What's the distance? 0.45 plus 0.15. That'd be 0.6 meters. 0.6 and 6, that leaves 10. And so we get that that's 90 volts. Then I need to do the second charge. I do it exactly the same way. I find V2 is KQ2 over R2. And I get 9 times 10 to the 9th Newton meter squared per Coulomb squared. I multiply this by a minus 4 by 10 to the minus 9 coulombs. Again, these two cancel. And then for the distance, it's a little different. I'm talking about this distance here. Well, this is an isosceles triangle, 0.45 meters on each side, and the hypotenuse I know is the square root of 2 times that. If you don't know that, you have to use the Pythagorean theorem. So this is 0.45 meters times the square root of 2. And now, of course, I need to punch this into a calculator. So I have minus 36 divided by 0.45 divided by the square root of 2, and assuming I've done this right, I get minus 56.57 volts. What's the total voltage? You just sum the two up. So V is V1 plus V2. So I get 90 volts. I just write it out. It's confusing to have V's and V's. And then subtract 56.57 volts. So 90 minus 56.57. And I get about 33.4 volts, at least to 3 sig figs. And that's how you do discrete charges. Compare this to the electric field, where you had all of these vectors that had to be added vectorially. So much simpler without the r-hats in any of this. Now, you have a similar type of problem to the electric field in dealing with problems that involve continuous charge distribution. Here they want me to find the electrical potential at a distance d to the left of this rod. This rod, which is uniformly charged with some amount of charge Q, let's say. So uniformly charged, this means that the charge density is Q over L. First thing to do is find this dq. dq is equal to lambda times the width of that box dx. So this box has a dq. It also has a width dx. We now put that into our formula for the potential. The electric potential is K dq over r. This would be k lambda dx. But I also need to write r in terms of x. Well, I look up here in my graph. R is d plus x. Then to solve the problem, what I do is I say that v is equal to the integral. Where does the charge start? The charge starts at x equals 0. Where does the charge end? The charge ends when I get over to L. This is x equals 0 to x equal L. K lambda dx over x plus d. I can bring the k lambda outside. So I get from 0 to L dx over x plus d. Now, this is an easy integral to solve because I can do a substitution. Let y be defined to be x plus d. Then dy is dx. X equals 0 is y equal d. X equal L is y equal d plus L. So to finish this problem, v is equal to k times lambda times the integral from d to d plus L of dy over y. This is k times lambda times the natural log of y, and that's evaluated from d to d plus L, which is k lambda natural log of d plus L over d. Again, notice how much easier it was to do these integrals because we didn't have any of the vector stuff. But we do get some interesting things. We don't just have polynomials like the 1 over x squared and such. We end up now getting natural logs. So things are changed a little bit from what they were before. Okay, we'll work another one in the next video showing how not to go from electric field to electric potential difference, but if I find the electrical potential difference, for instance, by this, how do I go and then find the electric field, which I didn't know? Here we just had to tell the charge. I didn't have to tell you the electric field. I want to be able to find the electric field, but not by doing the harder integrals, but by first finding the potential and then using the potential to find the electric field. That'll be on our next video.